consoles are really hard to get on. The main thing is so that your voice still works. Can you test it?
Hello? Hello, hello, hello?
Yeah, it's working.
Okay, so I should lean down a little bit when I talk.
Yeah, do you want me to talk about the lab deadlines when you talk about labs instead of after my intro? I can stay.
Oh, yeah, that would be great, actually.
Okay, so I'll just talk about it here.
Okay, I will give you the slides. But also, do a little intro on the slide countdown.
Sorry?
Come on, do like a little intro on that slide countdown.
Yeah, I'll do the intro and then I'll wait to it up. Don't even say that.
Alrighty, folks. If you haven't found a seat, please try to find a seat and then sit down. We'll have the lecture about to start. Can people in the back hear me all right? Good? Good. Okay. Thank you. Also, try to take a picture of this if you haven't, and then try to finish it before the next class, if possible. It's a very simple form so that just the teaching teams can know a little bit better about everyone's background and their class stance right now. Thank you. Alrighty, let's get started. Hi everyone, thank you for choosing this class, and then welcome to the 373 Introduction to the Embedded System Design. And this is lecture 1. We'll basically cover a little bit of the intro, and then go into the overview of the chip STM32 that we're using, as well as a little bit on the GPIO. So before the actual content, a few announcements. First, please fill out the intake survey that I just posted. The slides has already been posted on the class website. So if you missed that, feel free to check that out and then fill that. Try to do that before the weekend, and definitely submit that before the next lecture if you plan to stay in the class. And the homework 1 assignment will be due on the next Friday, on the 17th. And for this week, we don't have lab sessions, so the lab 1 will be starting next week. And during that lab, the pre-lab, which you will know in a bit what that means, but basically for next week only, the pre-lab will be due in lab. For the future, it's going to be due basically before your own lab session starts. And we have, unfortunately, 2 exams, and the date's already set, both on Friday, 4:30 to 6:30 on the 7th of February, and also the 14th of March. And we will be waiting on the locations. I'll let you know as soon as we figure it out. And finally, make sure you have access to the Grayscope as well as the Piazza. If you don't, come talk to one of the teaching team, and we will have that figured out for you. So for this lecture, basically, as we said before, we're going to have first the course overview, and then talk about what is an embedded system, and then we dive into basically a little bit overview of the STM32 architecture. It's basically STM32 is a family of microcontrollers developed by the STM Electronics, which is based on the ARM Cortex-M processor cores. These are the microcontrollers we're going to be using in our labs and most likely your final projects as well. And then we'll also give a quick intro on the GPIOs, general purpose in and out pins. So a little bit about myself. My name is Junyi Zhu. I graduated with a bachelor at University of Washington, ECE, concentrated on the embedded system. That's when I took the equivalent of this course, and I also TA'd that course there. And then after that, I went to MIT, EECS, and CSEL, Computer Science and Artificial Intelligence Lab, to do a PhD in computer science. And then I graduated June 2024, so like six months ago. And then I started my appointment here as a junior faculty at the EECS department about 9 days ago. So good to meet you guys. And some introductions on the other instructors and the teaching staff. First, we have the labs instructors, Matt and James. Do you want to come up and say a little bit? Just, yeah. They have enormous experience with the lab materials and also this course. So if you can't get an answer from me, please try to reach out to them. They probably have a better answer.
Yeah, hello everybody. Good to see everybody back at the beginning of the term. I graduated from Michigan's engineering school. It was a little while ago when engineering was still on Central Campus. So I won't date it any further than that. After I graduated from here, I started to work in what we would eventually call embedded systems. At the time, we didn't really even have that name for it. Microprocessors were just becoming accessible, that were actually being produced. So we were finding all kinds of applications for these low-cost, processing units. And there were a lot of effectively embedded systems or, application-specific stuff. So I got to see that change over the years. And I did that for a little over 20 years. My wife got tired of me traveling around the world, even though I liked it, and she found me a job here. And so I started in doing this embedded systems class when it was just in its infancy, it was just beginning. And frankly, the first year that I taught, I didn't think I could do it because I didn't know how to communicate to other people that weren't my peers about engineering. So, but I stuck with it, and I've been here for 20 years, and I'm still trying to work on figuring out how to communicate engineering to you. But I think I'm a lot better at it. So I think the course has really evolved over time. I think we have a really good course, and I look forward to working with you in the labs and for the projects.
I'm James Carl. I graduated here back in 2012 for computer engineering. So I took this course, took the 473 course that was after this one. Matt was my instructor back in the day. Then I was working at Ford for over a decade, and I heard about a position opening up. Maybe someone might be retiring at some point. And so I kind of jumped on it, and this will be my second semester here. So I look forward to working with everyone.
Okay, perfect. Thank you. Next, we have amazing team of GSIs and IAs, which will be, we have two of them, the GSIs here. We can have them up and briefly introduce themselves to you so that you know who to find. Here we have Anna and Joseph.
Hey everyone, my name is Joseph. I'm an EECS student here on the robotics track. So I've been a 373 IA before, as well as a 473 GSI last semester. And yeah, so my background is pretty much in software. I of course took 373 and 473 in the past. And yeah, look forward to seeing you all in lab and for a great semester.
Yeah, all right. So hey guys, I'm Anna. I'm also an ECE master's student here. I'm actually on the integrated circuits and VLSI track, but I did embedded in my undergrad, so I did 373, 473. I IA'd 373 with Joseph and also GSI 473 with Joseph. So yeah, super excited for this semester. Yeah, see you guys in lab.
Thank you. And we have two IAs, Alex and John. They're super amazing. They can't make it today, but you will meet them anywhere in the lab. They will be there all the time. And a little bit on the course goal here. Basically, after this course, you will learn how to implement embedded system, including like hardware and software interfacing. And then you will learn how to design embedded systems and how to like think about the software and hardware, how they work together, basically. After that, you have to opportunity to design and build your own embedded system, which is basically the final project of this course. Super fun. It's going to be time consuming. It's going to take you a month, but you will have something in the end to show off. We have a expo schedule for you guys so that you can show that to classmates and also basically to the entire campus, North Campus at least, which is basically. And then at the end, you will have like a foundation knowledge of enable like a lifetime of learning about embedded systems, because you will learn very soon that the concept of embedded system and which range it covers is actually a very dynamic field, so that whatever we taught you in this class might get outdated in like 5 years or 10 years, but we hope you have these framework and foundation of the understanding of the basics, and so that in the future, however the fields exchanges, you will still be able to keep up with the flow, basically know how to read the data sheet. Some of the prerequisites of the class, we have the 270 to introduction to the logic design, and 280 programming and intro to data structure. This is for like the C language programming, which we will be using mainly for this class. And then we have like the 370 introduction to the computer organization, which will have some basic computer architecture stuff, and as well as like assembly, etc. So for the architecture part, our course will be built on top of that. That will mainly focus on the core. We have like the core plus the peripherals devices that surrounding around the core, basically. And then, not like a prerequisite, but too good to know, some basic understandings of electronics, voltage, currents, what lights up an LED, what drives a motor, etc. And these will be basically very useful in the lab sessions, and as well as later on when you do your final project. But don't freak out if these sounds like very strange to you for now. It's going to be quite basic knowledge you need to know, and then we will help you along the way if you need additional help on that. So the topics of the class, basically, first will be Cortex M4 processor, the ISA, the instruction set architecture that we will be talking, I think, in the next lecture. And then the memory map NO, in and out, and then the interrupt and timers basically teaches you how to, or like how the event-driven that can cause things that happens to your embedded system. And then the common data bus and the device interfaces, basically how these different type of devices communicate to each other, like the through I2C, SPI, etc., how exactly they work underneath. And you will be working with the analog input and output. So you will have learned, ADC channels, analog to digital converter, and then D2A digital to analog converter, etc. Some of the class logistics, basically, embedded system is about like reading the menus, searching online, and finding answers. So if you find something, especially in the lab sessions, and then later on in the final project, if you find something that you can't figure it out, before reaching out to us, I suggest you Google it or ChatGPT. I think people said that Stack Overflow would be your best friend, or ChatGPT at this point. And there's no mandatory textbook for the class, but if you definitely want to read something, these two are the ones that are recommended. The first one is the embedded system with ARM Cortex, microcontroller in assembly language and C. I was told that this is a great book. I haven't read it. It's going to arrive tomorrow night. I'm looking forward to it. And that one is basically like a very, very detailed manual book, in case you want to explore more in depth how exactly this architecture and this chip works. A little bit on the grading. Basically, we have a little bit on the class participation, which will be used as like handout forms that you will fill out in class and then submit it into the grade scope. Basically, it's like a pass, no pass. So you get the credit or not credit, unless you really didn't do anything on that sheet. And then we have the homework, 7 homeworks. And then labs, which is a pretty big portion of the course. And then 2 midterms, student presentation, which is, we'll talk about it in a bit. And then final project, which is like a big chunk of the grade. Mainly things that determine your final grades in the past years are the project and the exams. And generally, class median would be like B+, and then or A- if you guys are really great. We'll see. For the lectures, yeah, as I said, basically we will teach you like overviews and like high-level concepts of the embedded systems and how to learn and learn these concepts. And then, yeah, the class participation, basically. Oh, one more thing on the class participation. If you answer a lot of questions on the Piazza, that also counts as participation. So it's basically a course involvement plus the Piazza activity. This is the class schedule. It is on the course website right now. It's a very living schedule. So anything that we made the change to that, we will obviously make announcement in the Piazza, but just keep an eye on that in case anything that slightly changes. Homework exams, 7 homeworks. I was told it's smaller than before, but smaller than last winter probably, and it's designed to give you practice for the exams and labs. And exams, these are the 2 dates that we mentioned before, location TBD, both on Friday and 2 hours. Please try to block out that time in advance. We will be, unless you have like some very special circumstances, we will be very hard to accommodate your, taking the exam at a different time. And most of the lectures will be will ended around like the week 10, so that you have more time to work on your final projects. And there will be no final exams, hooray. So, just final projects. And the lab session, we'll have our GSI, Anna, to talk a little bit more about that.
Okay, so in embedded, the best way to learn is kind of get hands-on experience. So the lab portion of this class is pretty non-trivial. I would say it's a pretty large part of the class, so it's important that you kind of like pay attention in them. There are 7 labs, and then each of them are a week long. So they end around week 8, right around spring break, and then after that, you guys will fully transition into working on your final projects. All the labs will be in room EECS 2334. Please go to your assigned lab section, especially this first week, just so that we know who's in what. Labs will be done in pairs, and then if there's an odd number of people, it will be done in groups of 3, but we really prefer pairs. Quick note about this week's lab. So this week's lab is going to start next week. The first lab, we're allowing you guys to have the pre-lab, in-lab, and post-lab due at the same time. After that, your pre-lab has to be done before your assigned lab section. And then your in-lab and post-lab will be due at the same time, 1 hour into your next lab. So let's say for lab 1, that means your pre-lab, in-lab, and post-lab will be due 1 hour into lab 2, if that makes sense. We'll talk about lab more as you guys go into lab, but yeah, that's something, I think that's the big important thing that we should know right now. Yeah.
Sounds great. Any questions so far? Okay, please.
Maybe not.
Oh.
When it says on the screen estimated around 6 hours per lab, is that the in-lab and post-lab portion, or does that include that?
That's probably the in-lab and post-lab portion, yeah. So your guys' assigned lab sections are 3 hours long, but they usually take more than that. So you'll be able to go to other lab sections or like open labs to finish them off.
Yeah, we have the room like 24/7 basically. So if there is no one there, feel free to go in and then finish. But try to keep it tight. I think it's going to be very hard, but let's try. A little bit on the student presentation. So basically, student in group of 4 will be giving a topic in embedded system and give like about 15 minutes lecture presentation to the whole class. It's like 12 minutes of the concept plus 3 minutes of the Q&A. Every student will be improve their presentation skills and learn how to communicate with a non-expert audience, which will be very, very useful once you become like an actual engineer or doing other, after your graduation, basically. And the team or like the group assignment will be based on your final project team, and then you can either pick a topic from some of the predetermined topics we picked, as well, or based on what you're going to work on for your final project, and some of these special devices you use or special sensing mechanisms that is different from the other classmate, and then you will be giving like introduction on that. And the big chunk, basically, open-ended final projects. The goal here is learn how to build like embedded systems, a working one from scratch. And then you're going to be working on a team of 4, the same team assignment as before. We're going to have to try to keep you at 4 or above, hopefully for all the groups, because we have more students enrolled this year. So that in order to have enough capacity from the teaching team to have enough interaction with each team to get to have like amazing final project in the end, we have to, keep you at 4, unfortunately. And that's going to be the major focus of the last third of the class. And I can't emphasize this enough. It's going to be very important to start early, although people are going to be deadline driven, but important to start early. And there's also a team formation event on the 14th of February, Friday, the same time, for like 4:30 to 6:30 p.m. Location TBD, a perfect date to start any relationship. And then we will require you to come unless you have team formed and also like a mini project proposal that's already ready. But you could leave early at 6 p.m. if you already have formed team successfully by then and can prove that you have a date scheduled. So we'll keep it a little bit light on when you exit. It's going to be a very significant time commitment. Assuming you will be spending a lot of time on this class. And, for the lecture, it's going to be 2 to 3 hours, and then 6 hours, like we said before, about like working in the lab. In total, across the entire semester, 20 hours, give or take on homework, study, and take the exams, 2 exams, probably 20 hours in total. And then 8 hours of your presentation. It's including everything, preparation, and you will have like a sit down with us to go through your slides and go through your concepts, etc. So big time commitment. Think twice. And if you do decide to leave the class, we still have a few people on the waiting list. So don't be shy. Yeah, average hours about 12 hours per week, basically. And in the last third of the class, it's going to be the more busy time. You're going to have probably 15 hours or more in overall for this class. We might cancel lectures at the time if necessary to give you guys more time to work on the final project. And after all those time commitment, which you get out of this course. So before this class, basically you have learned engineering mostly in like abstract concepts. And from this point on, you will be using these knowledges and then to solve the real world problem. And by the end of this course, hopefully you will have your first working, embedded system from scratch, and then take the very first step towards being an actual engineer. From the textbook to the real working system. So it's a very much transformative courses, and it's going to be very fun. All right, that's the class overview. Any questions so far? Okay, yes.
How are lab meetings? How like they would try to reach safety by like a week or something like that, or like something?
That's a great question, Anna.
They're due so if your lab's on Wednesday, your lab will be due the next Wednesday, 1 hour into your assigned lab session. Yeah.
Okay, cool. Let's move into the fun part. So, what are embedded systems? Short terms, embedded systems are everywhere. For example, like in transportations, in these times, often they are like computers without screens, without like traditional human-facing interfaces. For example, in the modern cars, you roughly have 100, give or take, different microcontrollers in in modern car. And then we also have, say, medical devices. Of course, they do have screens and input-output buttons and stuff, but they're built for very specific tasks. Basically, one device for that one, X-ray scanning or MRI, or give you ECG measurement, etc. And as well, of course, the consumer electronics, Wi-Fi routers, and nowadays, can you believe it, microwave also have all those, and then they will very much be considered as embedded system as well. And cameras, smart TVs, etc. Although they have sometimes they have OS on them, but since there are still very specific tasks, and nowadays we still consider them as the broad of the embedded system. A quick example here is the Google Nest thermostat. And what do you think are included inside of this one device or one module? So we have obviously the LCD display for displaying the stuff, like temperature, etc. And then we have like a rotary encoders, kind of like an input system. And inside of the chip, we have a bunch of stuff here. We have like a Cortex microprocessor, very similar to what we're going to use in the course. And Wi-Fi modules, another wireless communication, Zigbee, and then like some memory modules, and then IR motion sensors so that it knows there are people in front of it to light up, etc. And power management, of course, as well as battery. And temperature and humidity sensor, just in case you need to actually use it. So with all those functions packed, sensing components or BOM, bill of materials, usually cost around like $30 to $50. Of course, they sell for like $280. And that, my friend, is how you're going to get paid. So, but apart from that, why, can you think of the reason why so much technology is being packed inside this one thermostat? Any guesses or any thoughts on this? Okay, yes.
Connectivity between all devices in your home.
That is the perfect answer, yes. So they're trying to make like more like a smart home hub or something like that. That can be kind of like a Internet of Things stuff to control and talk to any other devices in home. That's why a lot of these communications on wireless, I think some of them even have Bluetooth, not this one, embedded inside this one system. So, a quick detour from the topic. So what's driving this technological innovation and how we get here? You've probably seen this before, but I'm gonna just do it one more time. Especially now that if you think about it, that one thermostat have more computing powers than back in the day when people land on the moon. Yeah, it used to be iPhones when I took the class. Now it became like a thermostat. Time have changed. How can we afford all these technologies packed in such a small form and be available for everyone? To start with, there is this term we call people per computer, or PPC. Basically, it means the number of computers each people has. It's been grows dramatically from back in the days, basically like the mainframe. That one big computer, basically, you can imagine like the whole University of Michigan have one of those. One computer, and then became each department have one, and then each lab, and then everyone now have more than one computer devices. Next is the volume, the size shrinks every decade. Basically, became like smaller and smaller, so that you are able to carry those and then fit more in the given space. And of course, the price falls dramatically. I don't have to remind you of these, but basically this is already adjusted and it's in log form, and just look at how things are changing. That's quite amazing compared to any other more traditional industries. So we have this, what we call like Bell's law. It basically says that every decade there will be like a new computer class that's pop out due to like usage or establish of a new industry. And there are actually ongoing discussions and explorations on what's new class of computer now in 2020s. And you guys will be part of it. And of course, like we have the Moore's law. Basically, every 2 years or so, the number of transistors will be doubled on the same size of the chip. It held for the past 50 years or so. It's kind of over now in terms of the number of transistors, but it's still ongoing in terms of like the performance or like cost efficiency with other approaches they're doing with the architectures or material advances, etc. And there's a trend in like wired and wireless communications, like the transmit speed. So basically you can see that the wireless transmission speed is going up, and at some point they're going to cross each other, and even possible that surpasses the wired solutions in some cases. And just think about like what can be designed then, like the type of new device can be enabled or computing class. And of course, there are like the material breakthroughs that led to the battery technology improvement. The amount of time kept the same amount of computation power alive between recharges, and the recharging time is also, that one is a little bit slower to improve on, to be honest, but that's also improving. So what's been driving this Bell's law? we have, as we said, like the technology scanning, Moore's law, standard scanning, and with the results of these two, basically we will have with the amount of the transistors number the same, it became lower cost and more efficiency in terms of the power. And other technology innovations, basically with more type of device being developed, like the displays, like memory, and like microfabricated sensors, as well as basically a bunch of things, as well as like new wireless systems, for example, like cloud computing, etc. included. And battery technology. That one is slowly catching up. Hopefully they will solve that soonish. So bear that in mind and then go back to the previous question, or like the previous Bell's law. What do you think is the next class of the computer will be? I'll give you like 1 minute-ish brainstorm on this, and then these are some of the things to keep in mind when you think about this question. And it could very much be something you already have, but just haven't been like greatly adapted. So we're talking something like kind of in the short-term future. Okay, please try to talk to your teammates or classmates, and then we're talking like a minute. Alrighty, okay. Anyone wants to share their thoughts? Oh, hello. Anyone wants to share their thoughts? Okay, guys. Anyone wants to share their thoughts? Yes. VR devices, very good one. And like the headset, you like mix see-through ones that the Meta is trying to push through. Nice. So you're a big believer in the metaverse. Nice. Okay. Who else? Oh, just on top of that, how much do you think the cost would be before it became like, just a side question?
I'm thinking it's going to be around like how phones cost like at some point.
Mm-hmm.
I think it might be slightly more expensive,
Mm-hmm.
but it goes around there.
Yeah, that's a good observation, I think. So it's going to be probably a little bit more expensive in general. It could be a bit more expensive considering how we grow from the previous, say, like more analog phones to like more smartphone. The price is actually increased by at least 30% or like even 100%. Any other thoughts on the next class? Yes?
Perhaps technology that's integrated with our body, like a brain chip.
Like the Neuralink? Nice. That might be a little bit longer than 2020s, but we'll see. You never know what Elon is capable of nowadays. Sorry, what's your name?
I'm Sean.
Sean. Okay, and what's your name? Shamil. Okay, yes.
I was thinking something like along the lines of like holographic AR, but without like vision or VR. So that way you wouldn't need to buy a headset, you just buy something that like projects it, and then it could function like a computer.
Like a AR glass that have like little projectors on the side to keep
No,
you.
like an actual like hologram that projects it out, and then you don't have to like wear anything to see it. You just have a projector.
I see. And did you carry it, like wear it on the body, or like
I
a?
was curious with you.
I see. That's yeah. That could totally be possible as well. And yes.
With breakthroughs in healthcare, some sort of devices that checks like your overall health,
Mm-hmm.
like just many things combined, not only like blood pressure, whatever, but like perhaps if you have any sicknesses or something.
That's a very good idea. That happens to align with my research topic as well, with my lab. Cool. So yeah, those are
Can I say another one?
yeah, of course.
I was gonna say like quantum computers, they're like a bit of a niche, but like there's been major progress with like quantum computing.
Yes.
Like, integrated.
Yes, that is a very that's a very interesting thought. I think as far as I can understand, so the quantum computing works differently with the current traditional computers and like what they call quad bit rather than the current bits we have. A very common understanding of people is saying that it's going to solve the parallel computing problem, but that might not be true. It's actually very tailored for specific applications. So it's even, I'm not trying to shut you down or anything, but realistically speaking, even when we have the quantum computing, likely the daily tasks we have is still going to be done with deterministic machines that we have right now. Those will be used mainly for like some simulation in physics or etc. for them, or like fluid simulation. Cool. Okay, let's. This one sounds much more boring than you had. Basically, one possible answer the teaching team come up with is obviously one of the mobile devices without like traditional use case and connects to the internet and backed by like cloud computing. Especially so instead of like more general purpose like your phones today, it's more like it could be something like Google Home, Alexa, more ambient, and then something might be. It could also be like conversational based. Now that the huge demand is in the LLM, so and of course AR, VR glasses and projectors that have been carrying around, and but either way, we're willing to beat that the embedded system. We play a big part of it in the next wave of the computing, because you will also learn the concept that changes with the time. So what is exactly an embedded system? If we come to look at some of the most obvious things, I guess, to our audience, like a gaming PC versus like a gaming console. So these are some just comparisons here. We will consider a gaming PC as not an embedded system. It's basically a general purpose computing platform, computing machine. And the game console, we will definitely consider it as an embedded system because it's used for basically designed for the gaming. Of course, it's you now have like OSs on it. You can watch movies, etc. But it's still like one device that built specifically for this purpose. And then compared to like more general computing devices, these devices tend to be lighter or cheaper or like more power efficient. So yeah, embedded systems is about making trade-offs between optimization and cost for like a particular application. So is mobile phone an embedded system? Let's have like a 30-second brainstorm or discussion on that. Okay, any thoughts? Any thoughts? I'll give other people some chance. Any thoughts from other people? Do we have an answer? Alrighty. Anyone want to share the answer? Anyone? Come on, this is the first day of the class. Okay. What's your name? Sorry. I'm Jim. Okay, cool. Go ahead. Mm-hmm. That's a very good answer, exactly the one I'm looking for. So what year you were capped on this spectrum, where you have to draw the line between an embedded system versus non-embedded system? You know, another 30-second discussion, and then let's, any thoughts on this? Alrighty. Any thoughts? Okay. What's your name? Casal. Okay.
I think just 2003 is where the switch happened, where it became like a general purpose computer, not an embedded system.
So after the 2003, what's your reason for that?
It's because after that, you could do much more than just calling someone, so it doesn't have one purpose, so it has probably multiple embedded systems inside of it, connected to the internet, using a camera, calendar, media playback, there's a keyboard.
Sounds good. Yeah, that's a decent answer. And what's your name? Sorry.
Mine?
Yeah.
Chris.
Okay, Chris. Yes, please go
I
ahead.
would say 96.
96.
I
Wow.
remember playing the Snake game in the 2000 version of the Nokia.
I see.
So if you can play a game on it,
I see. That's a good point. But also think like before when we talk about like game consoles, it can obviously give you play games, which is the main task, but also allow you to do a little bit other stuff like, watching movies and stuff. So I think, obviously this is like open-ended questions here, but I think we will argue that the 2008 is pretty much where it happened. And the reason for that is the release of the App Store. So basically, that's what makes the whole ecosystem open, and you can be any developers can join and then push their own thing into this device, rather than previously. It's obviously can do a lot of stuff, but it's more or less pre-packed. Like other people or other teams does not have like impact on what this device is able to do after it's shipped out of the factory, for example. But even with the first generation iPhone, but like after a couple of generations and after the release of the App Store, that's really what make in our term. Of course, it's an open-ended question, but what makes the whole phone platform become more general purpose. So what about then auto vehicles nowadays? Any thoughts? You can just shout out your answers. Any thought on this? Autonomous vehicles? These are embedded systems? Yeah. That's a good call. Any other thoughts? Yes.
With the advent of things like Apple or whatever, CarPlay and that kind of stuff, you are kind of opening it up to like outside developers and kind of getting that same iPhone, like general computing kind of thing. Obviously, there's only so many things you want to do on it, but even like a Tesla these days, I mean, the computer system in there basically will run whatever. So I think on the whole, it definitely looks like an embedded system, but they definitely have the capability of being general purpose computers, and they kind of are going that way a little bit. So I think it's a little bit of a mixed thing.
So like a combination of both. That's yeah. I think both. Yes, both answers are correct, and because we have all kinds of sensor systems around it, and then we also have like a more central control, so to speak, that controls all of these. So we will argue that it is like a collection of embedded systems inside of this auto card nowadays. Okay, a little bit less obvious one. What about an SD card? Okay, you might want to discuss a little bit on this.
Yeah, because it's not a system it's by design. It's the hardware that does that. Yeah, it's
All right, we have any thoughts on this? Any answers? Okay, one more time. It might be end.
Maybe it's more like here, but like.
Sorry, can you speak a little bit louder?
Maybe
So
it's
that,
my more limited knowledge, but like the one thing I think about for like an SD card is like storage and stuff. That's really hard to think about for cards. I don't know if they can do more than that. So I'm thinking, okay, so there's systems, since it's the last specific task.
I see, I see. Wait, so, but if it's like that, then would a book be also considered as an embedded system? We'll keep thinking on that. Any other thoughts? Is it getting late in the day, or any thoughts, folks? Okay, yeah.
What are you doing? Like, you need something to interface it, unless you somehow know how to read, like, data and stuff. There's nothing to do with content.
That's a good argument. We'll get back to that. That's a very good argument. Any counter argument to that? Yes.
I don't remember if SD cards do have a memory controller on them, but there is probably some microcontroller on there doing some of the like communication and setting up however it's communicating from the system. So I would argue that it has some controller capability for very specific hardware on it. I don't know if SD cards are just like static memory, they don't have anything else going on in them, but I don't think they do. Like I think they do have it.
That's a very good point. I think that kind of answers the previous, like just the storing or compared to the books. So compared to the books, these things can be input and output basically of this one's SD card. So their chances are there probably some kind of control systems on the chip, right? So, in fact, they are indeed, embedded systems, and the reason for that obviously is has the communication protocol. They have actually a dedicated MCU microcontroller inside of each of the SD card nowadays. Reason for that, first is for the communication, and more importantly, it's for like the workaround around like error collecting code, because it's actually these flash memories are quite unreliable, and then in order to make sure the data you stored, even you have like some bits or bytes off, it still have the correct data. Then we need like a special embedded controller in every basically of these devices. And they usually are like in like 7 or 80, 51 controllers inside. So how, with all that examples and the discussions we have, can you try to come up with your own definition of the embedded systems? And another discussion. We have a couple more discussion, but that's pretty about this. But anyone wants to? Okay, keep the discussion for like 60 seconds, and then we will share 3 to 5 definitions together. Imagine this is a very open-ended, so anything that makes sense and then align with the general people's thinking, that would be good. Go ahead. Alrighty. Do we have any thoughts? Anyone want to share their definitions? Take the brave first step. Yes.
We thought of an embedded system as being a closed electrical system with some type of logic like control.
That's a good definition. I think it's a little bit, it's quite broad, but that's a very good start. Yes. Any other additions to the definition or bring out from a different perspective? Yes. Wait. Okay, you're not raising hand. Never mind. Anyone else? Okay.
I feel like adding on to that definition, embedded system should also be used to like support or optimize a single task, like how that is in like
Yes. Also keep in mind that was like the last generation of thermostats. Nowadays, it also does a bunch of other things. Right? So maybe we could be a little bit broader than that. But keep in mind the definition of the embedded system is a very dynamic thing. You know, basically it depends on how much computation powers we have, and then how much power we are able to work around with. And this concept is being growing, just as how more tasks, more general computing, can cover nowadays. So let me show you, I guess, first some of the textbook definitions. Do we have some favorite ones? So first is a digital system that provides service as part of a larger system. I guess what that means is it's kind of doing a separation between, a more general purpose versus a single specific purpose. It's kind of like what we brought up in our discussion. And for the third one, less visible computer, I will argue that be careful of these super short definitions. They usually look quite striking, but if you think more about this, it have less content in it because it have less content. Do we have some favorite one of these? Okay. I'll point to a few parts of it. For example, the fourth definition, a single function tight constraint reactive computing system. I will ask you to emphasize on the reactive part. So basically, it means real time. So usually embedded systems are sitting there and then react to the surrounding environment or waiting for some event to happen and then trigger the system to do something. And then obviously we have the Wikipedia, which I think I would say is a pretty decent definition. Also a few slides on when embedded system can get really weird. This is the RFID tags that you see in most of the areas when you do shopping or to open garage doors, etc. It basically is a passive sticker and then take the energy from the antenna and then when it's being activated and then send back the data. And usually it's a serial number and then show its ID. And there are researchers working on this to make it, to basically harvesting this energy, the same principle as our RFID, and they use the energy stored together to do a little bit more than that. they embedded sensors like accelerometer, and then it have like a little microcontroller on board to do some programming as being told to do. The chip is called WISP. This is like a very simplified diagram of like a block diagram of this internal chip. It has so C, like impedance matching, rectifier to convert AC signal to DC, and then the power management, as well as we have the accelerometer and then temperature sensor, which is what the power is being used to driven. And then it has no battery. And this is like a quick demo video to see basically, by the moving of the chip, which is the accelerometer on board, it kind of controls a sound that's generated by speaker. This is done by UW system, like sensor system labs, while Professor Lanson Sample was there. He developed this board together with Intel, and then I actually used this sensor for my undergrad capstone and thesis. So, small world. A key takeaway here for the embedded system. So they are technological and market forces to drive the evolution of the computing, which triggers the development of embedded system. And these, by specializing these computing powers, embedded systems enables new computing devices that's not previously possible, including some weird cases we just show. And as I kept on saying, there's no precise definition of embedded system, but after this class, you should be able to identify one once you see it. Any questions so far regarding embedded system, like what is it, etc.? All right, perfect. Okay, next we're gonna go a little bit into the STM32 architecture overview. This is gonna be very quick. We're just gonna run through. If you don't understand some of the terms, that's totally okay. That's gonna be basically what the next series of lectures are on about. So basically, it's just served to give you like a very, very high-level understanding of the Cortex M4 architecture. So this is the board that's will be included inside of your lab div kit. It has the ARM Cortex M microcontrollers on it, so that you can use that to program and drive any other sensors or devices that's connected to it. This is like a simplified architecture diagram of this. The green part in the circle, basically it's the core, which is what you learned or supposed to learn in 370. I know some of you haven't taken 370. I think that should be okay because we're gonna focus on anything that's not that in this course. So apart from that, we have like memory system. We will be talking that in next lecture, memory in and out, and then different type of memories. And then they are all connected by buses. So buses are basically the method inside of the chip to sending large amount of data throughout the system, in and out. And all the buses are 32-bit wide, turning by the name STM32. And this is like a basic how it looks like in a parallel buses. If you did take the 370, just remember from the previous courses, it's essentially a bunch of D flip-flop putting together in parallel, and then we have like one clock connects to all of them, and then every clock we have like update on the data in parallel, so sending or reading. And we also have what we called two peripheral buses, one high performance and one just like a normal advanced one. Basically, what they're meant for high speed data versus like low speed data. And the high speed data on the top, like the AB buses, that's basically used. Oops, sorry. Yes, so it's actually on the bottom. The high performance ones are usually used for like more performance critical components like CPUs or ARM and other advanced peripherals. For example, like cameras, etc. GPIOs, when you want to have like something real fast. Remember we talked before, it's like a reactive system that responds to events real quick. And then we have like the more general peripherals, the APB basically handles general purpose devices and low speed devices. It's more latency tolerant and doesn't break as easy. So it's okay if it have some misbytes, etc. And we have interrupt, basically. It's, yeah, it's basically the way of stopping normal process of instructions and to do other tasks. Generally, this is what happens when you have like an input. For example, like user press a button and something happened to the system. This is what is going to be triggering. And for example, like say we want to load the content of R1 into register R0, and then what the system will do is basically it will take the data and then fetch it and then decode it, then pull from the memory into the core and store it somewhere. Is that clear so far? Any questions so far? Okay, cool. I know the animation is going to work great. And then another example for like the storing, pretty much the same. You fetch data, decode it, and then send the data to something. In this case, it puts in the timer. Timer. There we go. Okay. And all these communication happens through like buses that we talked about before. So this is the real block diagram looks like. It's basically identical as what I just showed you. Don't get scared. It have the same components in it, just it's being much more complicated because it is indeed a much more complicated design than the block diagram we show. So you will be able to, after taking this class, you will be able to read this more, detailed block diagram and then be able to understand any of the new systems that's coming out and which you're supposed, or which you're able to do with it, with the given capacity that the chip provides. Yeah, just color-coded to be the same, buses and the cores, and then we goes to these much larger peripherals and stuff. Okay. Still holding up all right? Okay, cool. So next we will go through the GPIOs, like a quick introduction to that as well. You guys sure you don't have any questions? I'm not trying to push any question, but just to make sure everyone was. Okay, cool. A quick intro to the GPIOs. GPIO, or like general purpose input-output, is so this is a ICs you will be having, very similar to the ones you will have in the lab. Basically, what people do is they take that little chip and then put inside of like a wire bonds into it and put into like a square package. And the wires, like these little gold fine wires that connects to each of the little pins and then extend it out to the little leg on the side, which we will be using for soldering. That's what connects to those pins. And a bunch of them are GPIOs. So remember, like from the previous diagram, these are where the GPIO peripherals are. And then it basically is sending or storing like 0 and 1s. And then, or like analog signals, depends on how you configure it. And then you can use it to do various stuff, for example. Of course, turn on and off an LED. And other cool stuff. Yeah, so basically, whatever the signal, the data there, it's got to be sent to like the registers, and then the system can quickly react to it. And also remember, like, what a register is. A bunch of D flip-flops and clock, 32 of them in our case, sending data in and out. Still holding good? Okay, and same with the storing. Data comes in and then the registers, and then it goes to be stored somewhere in the memories or send it out to other pins as the output or other peripherals, anywhere in the system, basically. And the only thing very important here is you will be knowing the address of each of the register, like where exactly, or in the memory, like where exactly you need those data to be. And these are typically can be found in the data sheet. This is like a very simplified output pin for like a GPIO output configuration. So the little bluish purple square here is the boundary between the chipboard and the outside real world. And basically the data in from the high performance process, as we discussed before, and then once it's being triggered by the clock, and then it goes to the I/O pins to the outside peripherals or any sensor modules. And then for the simplified version of like the input, it's basically a different type of D-flop. I just switch it so that to let you know that it's a different type of configuration. And then the data basically comes in and sent to the high performance buses, and then to registers, etc. If we put them together, this is essentially what it looks like internally. You can control it to be an input-output with this register control here. Basically another control signal standing up from the high performance that determines where that data goes to. Is it an input or to go to the top, or is it an output to get the data from the high performance buses and then to the outside world? And this is a push-pull pair, basically. You can think of it like a fancier version of switch, like basically a couple resistors putting together. The advantage of this compared to like a normal switch is you can use like a small amount of current to drive a much bigger amount of current system. So it allows more current passes. In our case, I think it's about like 10 to 20 milliamps tops for the systems we will be working with. Are you doing all good here so far? Okay, cool. All right, so let me show you a tool called FastAdd. It's basically like a current, like a circuit generator online. We built a couple things here to show you. This is like a GPIO switch LEDs. These will be posted on the website, so it's okay that, and also feel free to play with it. So where are we? Okay. So this is like an input version of the GPIO, and then if I just toggle this, you'll see the current goes, the signal goes through, and then turn on that LED, and then the signal down there you can see also got turned on. So this is like a digital control. Then this will be very close to what you do in like the lab one. Okay, exciting? Not so much. Okay. This is like the hello world moment of your embedded system journey, to just let you know. Like when you get that first LED light up. Okay, and also you can play around with settings in this tool. So feel free to play around with it later if you have any questions on like the circuits you build, etc. Feel free to use this tool. And we also have another more realistic version of the GPIO. So remember, this was like the block diagram that we have. Have both of them to be input and output in one GPIO. And this is the GPIO port example that we built for you, which is here. Can you guys see this correct? Like all the way in the back. Can you guys see this? Okay, perfect. So say like before, let me go fancier. So this is like similar to before. So if I connected the switch to and then I would change this to low. This is the register controller for like input and if it's in the input or output mode for the GPIO. And then I would just put it down, and you will see on the top here, it became high once I put down the switch. That basically means this current configuration is in input mode, and it takes the data we get from outside world. And then once the clock got updated, that's when the signal showed up inside of the bus. And that was the representation of what it looks like. So, and if we do like a output mode, of course we have to first turn it up, And then, so this is the signal that's being, like the high signal that's connected to the output. So it lights up one of the LEDs. And if I turn it to low, amazing, it lights up another LED. So, you know, this is basically how a GPL works internally. Do you have any questions so far? Or is it still good to so far? All right, great. No one's going to drop the class, I guess. Okay, cool. So that's pretty much the like a introduction on GPLs. And as we said before, it might be helpful to have a little bit more like knowledge on the electronics side, circuit side. So if you need any of the circuit reviews, etc., these are some sources you can go through. And then you can also come to office hours or to open labs to talk with, you know, Matt James and other like TAs or me to get it, and, you know, keep together. All right, a quick recap of the lecture today. So first we go through like the general course overviews, and then please do go see the website for more details. And then if you see any missing information, ask questions. Don't hesitate in Piazza, preferably. And then we talk about like the embedded system concept. What's the like the technology and like market forces that drive the development of embedded systems. And you know, in the end, you will be able to identify embedded systems when you see one. Although the definition itself is still kind of like a dynamic, evolving concept. And we also did like a very high-level architecture overview over the STM32, which was going to be the one you use. I actually have it with me, so just in case you guys want to see it. So this will be the board you'll be using. It's going to be your best friend for the next 3 months or so. And big takeaway here is, you know, load and store into the special register to control the chip, which is the example we get. You're going to have some practice of these in the homework as well as in the exam one, after we talk more about like the memory in and out. And, you know, we give you like a refresh on like the push-pull circuit architecture on the GPIOs, and then please do start read lab now so that you can get some of the concepts ready, and then when you go to lab one, it's going to be much more smooth for you. And next lectures, we're going to talk about the ARM Cortex and instructor set architecture, ISA, and some of the assembly. Hopefully, you mostly already learned it in the 370, but if you're not, it's pretty basic stuff, so it should be okay, as well as some application binary interfaces. Yeah, that's it. Cool. Thank you so much for coming, and then let us know if any questions comes up in Piazza. Thank you.
there's like the process to go off to and like when I take exactly this a part about like virtual memory and also like the cache. So we're gonna be like dealing with that like dealing with that page or like I mean the virtual memory page and also like soft cache stuff. Deal with them.
It's the memory system. We could put some memories in that. But it's
so like when we're like loading some or storing some addresses, we have to do like any like cache stuff, like loading from not a specific physical address.
I think like our project should just
virtual disk. So basically it's just like when we're like loading and storing.
everyone gets cancer. Just like it's like 3 times. I don't want to.
I just received the class like 2 years ago.
Yes, you just take the process and you throw it at like cut it into like a ninja
lectures, for lecture.
just don't power the processor. Just like grab it, like stick it like a disk of like that's it. That's
also have
there's a box of pain from doing. Okay, imagine like a red box, like a hole in this final project. Put your hand like take your hand out.
But when I talk to like a manager, they have been
so much. Lights.
Can ask like someone else to 1:30 p.m. 21. Each one says yeah, dude. It says 4:45. It's actually 14.
Like the witness of people who didn't know my points are here.
It's
yeah.
I think he doesn't even fucking truly know. He doesn't know what he was doing.
Yep.
To the fucking kids fire distribution cloud
If you have like
Oh.
yeah. So the problem how many users OS? Everyone but Julian, like 80 people in lecture, everyone was going to do hard shit. Like, he's good.
The lecture's directly mapped to the person. Okay, gotcha. Alright. So I'm registered as a professor. I just want to make sure that I can't switch that